The world ocean is the single, continuous body of water that envelopes our planet, covering more than 70% of Earth's surface and holding the vast majority of its water. Though we often divide it into familiar names, the Pacific, Atlantic, Indian, Southern, and Arctic, these are not separate entities but interconnected parts of one immense system. It is the defining feature of Earth when seen from space, a shimmering expanse of blue that gives our planet its nickname, the Blue Planet. More than a backdrop to human history, the world ocean is a living force that regulates climate, sustains countless species, shapes weather patterns, and provides the foundation for life itself. It is both a source of wonder and mystery, containing depths largely unexplored, ecosystems still being discovered, and secrets that stretch back to the origins of the Earth. To study the world ocean is to study the pulse of the planet, a vast and dynamic realm whose influence extends into every breath we take, every drop of rain that falls, and every grain of sand shaped by its waves. The oceans cover about 70% of the Earth's surface, a fact that shapes nearly every aspect of life on this planet. From the perspective of space, when astronauts look down upon Earth, what they see most vividly is a planet cloaked in blue. The vast expanses of water form an unbroken skin across continents and islands, linking together the poles and the equator. This enormous presence of water is not a mere detail of Earth's geography but one of the defining features of the planet itself. Without the oceans, Earth would not be what it is, a living, breathing sphere teeming with extraordinary diversity, a rare place in the known universe where life flourishes in abundance. To think of 70% is to recognize how water overshadows land in scale. Land appears to us as the primary setting of human civilization, with cities, farms, and roads stretching across continents, yet when measured against the sheer breadth of the seas, the terrestrial surface becomes almost secondary. The Pacific Ocean alone, which is the largest single body of water, spans more area than all the continents combined. This means that when we talk about our world, we are in truth talking about a water world, a planet where oceans are the rule and land the exception. The concept of Earth as a blue planet comes from this reality, the way the seas dominate its physical form and determine the conditions under which life is able to thrive. The oceans are more than mere geographical coverage. They hold an immense volume of water that acts as the foundation of Earth's climate system. The sun's energy pours into the surface of the seas, warming them in varying degrees depending on latitude. The warm waters near the equator store and release heat, while currents distribute this energy across the globe. This circulation of heat moderates temperatures, preventing equatorial regions from becoming unbearably hot and polar regions from turning into even harsher, frozen deserts. The presence of water covering most of Earth allows for this regulation, a balancing act that sustains the conditions needed for life. Without oceans occupying such a vast area, the climate would swing between extremes, and the stability we depend upon would vanish. The influence of the oceans reaches into the very air we breathe. Phytoplankton, microscopic organisms drifting within the sunlit layers of the sea, photosynthesize in the same way that plants do on land. In the process, they release oxygen into the atmosphere, providing a major portion of the supply that all animals, including humans, rely upon. The oceans, covering 70% of the surface, thus function as a hidden forest of sorts, a massive generator of breathable air. This connection between the unseen microscopic life of the seas and the functioning of terrestrial creatures highlights how integral the oceans are to the web of existence. Beyond their biological contributions, the oceans shape the human imagination and the course of history. For millennia, people have looked to the horizon where the sea meets the sky, feeling both awe and fear at its immensity. The 70% coverage meant that the ocean was not a boundary but a vast highway, carrying ships and ideas, goods and cultures across continents. Trade routes, discoveries, and migrations were all possible because these expanses provided paths between distant lands. Civilizations rose on coasts, flourishing through maritime connections. The seas became symbols of mystery, danger, and opportunity, inspiring myths of sea monsters, stories of lost cities, and poems about the endless waves. The fact of the ocean's dominance in surface area echoes through the stories we tell and the way we imagine our world. The scale of the oceans also reminds us of how little we truly know. Covering most of the planet, they form an environment less explored than outer space. Deep beneath the surface lie trenches, mountains, and ecosystems that remain shrouded in darkness. The Mariana Trench, the deepest known point, is a world of crushing pressure and eternal night, and yet even here life persists. Strange organisms have adapted to thrive where sunlight never reaches. Hydrothermal vents spew minerals into the cold depths, creating oases around which unique creatures cluster. Each discovery in these uncharted realms expands our understanding of life and challenges assumptions about where living things can exist. The ocean's vastness, which accounts for most of Earth's surface, is also a measure of mystery yet unsolved. When considering the oceans as 70% of the planet's surface, one cannot ignore the interdependence between them and humanity. The seas provide food, both directly in the form of fish and indirectly through the maintenance of ecosystems that support agriculture. They allow trade and travel, forming the backdrop of globalization long before the term existed. At the same time, this reliance makes us vulnerable to the changes that the oceans undergo. Climate change, driven by human activity, alters the chemistry of seawater, increases its acidity, and raises sea levels through the melting of polar ice. Since so much of the Earth's surface is ocean, the shifts happening within them ripple outward, touching every corner of the planet. Coastal cities face flooding, fisheries collapse, and storms intensify, reminding us that the oceans are not passive scenery but powerful, dynamic forces. The physical presence of water across 70% of the planet also influences the way we define borders and identity. Nations claim coastlines, draw boundaries on maritime maps, and negotiate rights to fish, drill, or sail. Yet the sea resists ownership in a way that land does not. It remains fluid, open, and immense, reminding humanity that much of the world cannot be carved into neat divisions. International waters stretch as zones beyond direct control, embodying the idea that some parts of Earth belong not to one people but to all. The ocean scale ensures it remains a shared expanse, a reminder of both common responsibility and shared vulnerability. The aesthetic and emotional dimensions of the ocean's dominance are equally profound. To stand on a shore and gaze outward is to confront something that overwhelms human proportion. The horizon seems endless, and the waves arrive in rhythms older than civilizations. The knowledge that most of Earth is covered by this expanse gives a sense of humility, reminding us of the smallness of human life within a grander system. The seas carry the colors of the sky, reflecting dawn and dusk, shifting from calm turquoise shallows to stormy black depths. Their vastness is both beautiful and intimidating, a paradox that resonates deeply with the human spirit. In essence, the fact that oceans cover about 70% of Earth's surface is more than a statistic. It is the central truth of our planet's character. It explains why life arose and persists here, why the climate is stable enough to sustain ecosystems, why civilizations develop through trade, and why myths of the sea pervade human culture. It is the reason Earth is called the Blue Planet, and the reason it remains unlike any other world we know. The seas are not background but foreground, not margins but core. To recognize their dominance is to recognize that the Earth is, above all else, an oceanic planet, and that our lives, our histories, and our futures are inseparable from the waters that shape the globe. The ocean provides around half of the oxygen on Earth, an extraordinary truth that is easy to overlook because the ocean appears to us mainly as a vast body of water, not as a source of the very air we breathe. We tend to associate oxygen with the forests of the land, the Amazon rainforest often called the lungs of the planet, the great belts of trees across Asia, Africa, and North America, and the grasslands that stretch across continents. While these terrestrial plants are indeed vital, it is the ocean, covering most of Earth's surface, that silently and ceaselessly produces about half of the oxygen that sustains life on the planet. In every breath a human takes, roughly 1 out of 2 molecules of oxygen comes not from a tree or a field but from the unseen work of the sea. This oxygen originates not from waves or salt water itself but from life within the ocean, particularly from phytoplankton. These are microscopic organisms that float near the surface, drifting with currents and tides, invisible to the naked eye yet present in numbers so great that they dominate the biology of the sea. Through the process of photosynthesis, phytoplankton absorbs sunlight and carbon dioxide, producing organic matter for their own survival while releasing oxygen as a byproduct. Individually they are small, almost insignificant in appearance, but collectively they perform one of the most essential tasks for life on Earth. Alongside phytoplankton, other marine plants such as seaweeds, algae, and seagrasses contribute, but phytoplankton alone accounts for the majority of oceanic oxygen production. The abundance of phytoplankton is tied directly to the ocean's expanse. Since the seas cover about 70% of Earth's surface, there is an enormous area exposed to sunlight in which photosynthetic organisms can thrive. In regions where nutrients are plentiful, such as upwelling zones where deep, mineral-rich waters rise to the surface, phytoplankton blooms can become immense, coloring whole stretches of the sea in shades of green or red. These blooms, visible even from satellites orbiting far above, represent colossal surges of biological productivity. In these bursts of life, oxygen is generated at staggering scales, feeding not only the creatures of the ocean but the atmosphere itself. What makes this fact even more remarkable is that it connects the daily breath of every person on Earth to the microscopic rhythms of the ocean. Whether one lives in a coastal town where the sea is visible each morning or in a landlocked city thousands of kilometers from any shore, the air one inhales is partly a gift from the ocean. The boundary between sea and sky is more porous than it appears, with gases exchanged constantly. Oxygen created by phytoplankton rises into the atmosphere, mixing and circulating with winds, ensuring that the work of distant waters sustains lungs everywhere. The significance of oceanic oxygen extends beyond human life. Every creature that breathes, whether through lungs, gills, or simpler systems of gas exchange, depends upon this cycle. On land, animals move through forests and fields supported by air enriched by marine photosynthesis. Within the sea itself, fish and invertebrates draw oxygen dissolved in water, oxygen that often originated from the same phytoplankton that forms the base of their food chain. The ocean provides for its inhabitants directly and for terrestrial creatures indirectly, creating a seamless continuity between ecosystems. The history of oxygen on Earth itself is bound up with the sea. Billions of years ago, when the planet was young, the atmosphere contained little free oxygen. The rise of oxygen, which made possible the evolution of complex life, came largely from cyanobacteria in the oceans. These ancient microorganisms, ancestors of modern phytoplankton, altered the chemistry of the atmosphere through photosynthesis, releasing oxygen that gradually accumulated and transformed the planet. The so-called Great Oxidation Event, more than 2 billion years ago, was born from marine life. Even today, the legacy of that transformation continues, as oceanic microorganisms remain central to maintaining breathable air. Yet the ocean's role as a provider of oxygen is not unchanging or invulnerable. The delicate balance that allows phytoplankton to flourish depends on the stability of climate, currents, and nutrient cycles. Human activities that warm the planet and acidify the ocean threaten to disrupt these conditions. Rising sea temperatures can reduce the mixing of water layers, limiting the delivery of nutrients from the deep to the surface where phytoplankton live. Increased carbon dioxide absorbed by the ocean alters its chemistry, making it more acidic and affecting the growth of certain plankton species. Pollution, such as agricultural runoff, can trigger harmful algal blooms that upset ecosystems and reduce oxygen levels in local waters rather than enhancing them. These changes raise a profound concern. If the productivity of oceanic phytoplankton declines significantly, the global oxygen balance could be affected. The interdependence between ocean life and terrestrial life is profound. When humans cut down forests, burn fossil fuels, and release pollutants, the impact reverberates into the seas. The oceans, in turn, reflect these pressures back into the atmosphere. The recognition that half of our oxygen comes from the ocean means that environmental damage is not just a local issue but a planetary one, directly tied to the survival of all aerobic organisms. Protecting marine ecosystems is not a matter of preserving beauty or resources alone. It is about safeguarding the basic life support system of Earth. Beyond science, there is something deeply humbling in realizing that our lives are tethered to invisible life forms adrift in the ocean. Phytoplankton are not majestic to look at, not grand trees or towering animals, but minute beings, many smaller than a grain of sand. Yet their collective activity sustains the breath of whales and humans alike. It is a reminder that life's foundations are often hidden in the smallest forms, and that the web of existence is bound together in ways that escape casual notice. The ocean, so vast that it seems eternal and inexhaustible, is in fact a living system of fragility and resilience, and its service as an oxygen generator is both a miracle and a responsibility. To understand the ocean as the source of half of Earth's oxygen is to reshape one's view of the world. It is to recognize that every exhale carries a connection to the sea, that the line between air and water is blurred by cycles older than humanity itself. It is to see the ocean not only as a body of water filled with life but as the planetary lung, drawing in sunlight and exhaling breath for all. The next time one stands on a shore and inhales the salt air, or even when breathing in the heart of a city far from the waves, there is an invisible bond with the plankton drifting in the currents. Their silent labor is what keeps the planet alive. This knowledge calls for awe but also for care. The ocean does not ask for gratitude, but it demands respect. Its biodiversity, its currents, its capacity to generate oxygen and absorb carbon are not limitless. If we disrupt these systems beyond repair, we risk suffocating the very cycle that sustains us. To speak of the ocean as the provider of half of Earth's oxygen is not just to marvel at its power but to recognize the urgency of protecting it. For as long as it thrives, so too will the air remain breathable, the climate livable, and the planet habitable. The ocean breathes with us, and in every sense, we are bound to it. The average depth of the ocean is about 3,682 meters, or roughly 12,080 feet, a figure that captures both the immensity and the mystery of the watery world that covers most of our planet. At first glance, numbers may feel abstract, but to imagine nearly 4 kilometers of water pressing down from the surface to the seafloor is to glimpse the vastness hidden beneath the waves. Most of us know the ocean only from its edge, where waves lap against the shore or roll beneath the hull of a ship, but the true ocean lies in the deep, far below where sunlight can penetrate, in regions that are more alien to us than the surface of the moon. That average depth, spread across an expanse that makes up 70% of Earth's surface, is a measure of a realm that defines the character of our planet. The figure 3,682 meters is not merely an average, but the product of countless peaks, valleys, trenches, and plains on the seafloor. Just as the land above water is shaped into mountains and deserts, forests and rivers, so too is the ocean floor sculpted into features both familiar and strange. Mid-ocean ridges stretch for tens of thousands of kilometers, forming the longest mountain ranges on Earth, while deep trenches such as the Mariana, Tonga, or Philippine plummet far below the average, reaching depths greater than 11,000 meters. Between these extremes lie abyssal plains, vast, flat regions covering much of the seafloor, silent landscapes of silt and sediment lying in darkness. The average depth of 3,682 meters reflects this blend of features, smoothing out the highs and lows into a number that hides the drama of the terrain beneath. To descend to such depths is to enter a world of extremes. Light disappears within the first few hundred meters, leaving the deep ocean in perpetual darkness. The temperature falls close to freezing, and the pressure increases by about 1 atmosphere every 10 meters. At 3,682 meters, the pressure is nearly 370 times what we experience at sea level, a weight that would crush unprotected human bodies and shatter most unreinforced structures. And yet life persists in these conditions, adapting to pressures, darkness, and cold in ways that defy imagination. Creatures of the deep are often fragile and translucent, built for environments where the weight of water is constant and the absence of light shapes their forms. Many generate their own light through bioluminescence, glowing in blues and greens to attract mates, lure prey, or ward off predators. The average depth of the ocean is not just a number, it is a measure of the alien world in which such life has evolved. Understanding the depth of the ocean has been a long human quest, born from both curiosity and necessity. For centuries, sailors used weighted lines, called sounding lines, to measure depths in coastal waters. These methods were crude and limited, unable to reach the vast expanses of the open ocean. With the invention of sonar in the 20th century, scientists gained the ability to map seafloors more accurately, using sound waves to measure distances and create images of underwater landscapes. Satellites today provide even broader views, measuring the slight changes in sea surface height caused by gravity pulling more strongly over underwater mountains or less strongly over trenches. From these methods, the average depth of 3,682 meters emerges not as guesswork but as the result of decades of careful observation and technology. The depth of the ocean also plays a crucial role in regulating Earth's climate and systems. Water at the surface interacts with the atmosphere, absorbing heat and gases, and then slowly sinks, carrying them into the deep ocean. This circulation can take centuries or millennia, locking away carbon dioxide and distributing warmth across the globe. The vast volume of the ocean, spread across those average depths, acts as a buffer, moderating changes in climate and stabilizing the planet. Without such immense depths, the Earth would not be able to store or distribute energy in the same way, and the climate would be far more volatile. The average depth is not only a geographical fact but also a foundation for the stability of life itself. The human imagination often compares the deep ocean to outer space, and in many ways, the analogy is fitting. Both are vast, dark, and hostile to unprotected human life. Both require technology for exploration and reveal environments strange and unfamiliar. Yet the ocean is closer, lying directly beneath our feet and coasts, covering the surface in plain sight. The average depth of 3,682 meters is less than half the height of Mount Everest, and yet descending into the depth is in many ways more difficult than climbing the highest mountain. While climbers contend with thin air and cold, explorers of the deep must endure crushing pressure and the absence of light, challenges that demand specialized submersibles, remotely operated vehicles, and robotic probes. To reach the bottom of the Mariana Trench, for example, only a handful of people have ever made the journey, fewer than have traveled into space. For all that difficulty, the depths hold immense significance. The ecosystems of the deep play a role in global biodiversity, supporting strange and resilient life forms that may hold clues to the origins of life on Earth and even possibilities for survival elsewhere in the universe. Hydrothermal vent communities thrive without sunlight, relying instead on chemosynthesis, where microbes use chemicals from the Earth's crust to create energy. These organisms suggest that life might also exist in similar conditions on icy moons like Europa or Enceladus, where oceans lie beneath frozen crusts. Thus, the average depth of Earth's oceans is not just a boundary of our world but a window into the possibilities of life beyond. The depth of the sea also influences human culture and imagination. Myths of sea monsters, stories of sunken cities, and legends of unfathomable abysses reflect the awe and fear inspired by the unknown beneath the waves. To look out over the horizon is to see only the surface, while knowing that miles of water lie beneath, concealing landscapes and creatures beyond perception. Writers, poets, and philosophers have long used the ocean's depth as a metaphor for mystery, for the unconscious, for eternity. The fact of its average depth gives grounding to these symbols, anchoring imagination in a measurable reality that is nonetheless overwhelming in scale. And yet, despite knowing the average depth, much of the ocean remains unexplored. More than 80% of the seafloor has not been directly mapped or studied. The average of 3,682 meters is therefore a kind of outline, a statistical truth that hints at more detailed stories still waiting to be uncovered. Within those depths are mountains taller than the Rockies, canyons deeper than the Grand Canyon, and plains broader than continents, all hidden beneath kilometers of water. To understand them fully would require generations of exploration, the building of technology more advanced than what we have today, and a commitment to unveiling the mysteries of our own planet. The number 3,682 meters is at once precise and yet symbolic. It tells us that Earth's oceans are not shallow seas but immense abysses, reservoirs of water and life that define the planet. It reminds us of the power of natural forces that shape the seafloor and the adaptability of creatures that thrive in darkness and pressure. It shows us how much remains beyond reach, how discovery still lies waiting beneath the surface, and how essential these depths are for the balance of Earth. To reflect on this average depth is to be reminded that beneath the waves stretches a world almost unimaginably vast, a hidden half of our planet, both familiar and strange, essential yet unknown, silent yet alive with meaning. Around 95% of the ocean remains unexplored, a fact that carries both wonder and humility. For all of humanity's technological progress, satellites orbiting planets, spacecraft traveling into the outer reaches of the solar system, and machines probing the surface of Mars, the world beneath the waves on our own planet remains largely unknown. The ocean covers more than 2/3 of Earth's surface, and yet most of it is hidden from direct observation, cloaked in darkness, pressure, and mystery. To say that the ocean is unexplored is not just to speak of geography, but of knowledge itself, of how much remains beyond our grasp in the very place we call home. The reasons for this mystery are not difficult to see. The ocean is vast, and the deeper one descends, the harsher the environment becomes. Light from the sun penetrates only a short distance, leaving most of the ocean in perpetual darkness. Pressure increases by about 1 atmosphere every 10 meters of depth, so that by the time one reaches the bottom of the Mariana Trench, the deepest known place in the ocean, the weight of the water above is more than 1,000 times greater than the pressure at the surface. Temperatures drop close to freezing, and conditions become hostile to most human technology. These physical barriers make exploration difficult, expensive, and dangerous, limiting our ability to probe beyond the shallows. What little we have explored has revealed that the ocean is far from empty. Submersibles and remotely operated vehicles have uncovered worlds of astonishing diversity and strangeness. Coral gardens bloom in deep waters where sunlight never reaches, illuminated instead by the faint glow of bioluminescent creatures. Hydrothermal vents spew mineral-rich plumes into the dark, supporting ecosystems that do not rely on sunlight at all but instead on chemical energy. Trenches and seamounts hold creatures so unusual they seem like beings from another planet, fish with transparent heads, jellyfish that pulse with rainbow light, and organisms that can survive crushing pressures and near-zero temperatures. Every expedition into the unexplored parts of the sea reveals new species, new geological features, and new mysteries, suggesting that the 95% yet unseen could hold wonders beyond imagination. The unexplored ocean is not only about strange creatures or alien landscapes, it is also about understanding how the Earth itself works. The ocean regulates climate, drives weather patterns, and stores heat and carbon. The deep currents that flow like rivers beneath the surface are part of a planetary circulation system that shapes the stability of the atmosphere and seasons. The chemistry of the deep ocean influences the balance of gases in the air, while tectonic activity beneath the seafloor gives rise to earthquakes, tsunamis, and volcanic eruptions. By not fully exploring the ocean, we leave gaps in our knowledge of the planet's most fundamental processes. It is as though we are reading a book with only a few pages visible, while the rest remain closed and unread. The unexplored nature of the ocean also invites questions about resources and survival. Vast mineral deposits lie on the seafloor, including manganese nodules, rare earth elements, and metals critical to modern technology. Hydrothermal vents accumulate sulfides rich in copper and gold. These resources could one day prove essential, yet they remain largely untouched because of the difficulty of access and the unknown consequences of extraction. At the same time, the unexplored ocean is a reservoir of potential medicines. Marine organisms produce chemicals for defense, communication, and survival under extreme conditions, and some of these compounds hold promise for treating human diseases. The uncharted 95% could be a storehouse of cures and innovations, waiting to be discovered. And yet, there is a paradox: while so much of the ocean remains unexplored, human activity is already altering it. Climate change warms its surface and increases its acidity. Pollution flows into its waters from rivers, plastics accumulate in its gyres, and oil spills stain its coasts. Fishing fleets sweep across its shallows and even into its depths, depleting populations before they are fully understood. We are changing an environment we do not yet comprehend, transforming the unexplored before we have the chance to know it. This ignorance carries risk, for without understanding, the damage could be irreversible, unraveling ecosystems and processes on which all life depends. The fact that 95% of the ocean remains unexplored also changes how we view ourselves. It humbles the human sense of mastery over the world, reminding us that our knowledge is partial and incomplete. We have mapped mountains, rivers, and skies, and yet most of Earth's largest habitat remains hidden. In an age where information seems limitless and boundaries constantly receding, the ocean stands as proof that mystery still surrounds us, that discovery is still possible, and that wonder still lies close at hand. When people imagine exploration, they often think of rockets and distant planets, but the ocean suggests that the greatest frontier may be here on Earth. The deep sea is alien enough to challenge imagination, its landscapes unfamiliar, its creatures astonishing. Yet it is also familiar in its importance, tied to our air, our food, our climate, and our survival. To explore it is not only to satisfy curiosity but also to secure knowledge essential for the future. Technologies continue to advance: autonomous vehicles, deep-sea drones, and improved sensors offer new possibilities for mapping and studying the depths. With each innovation, the possibility of shrinking that unexplored 95% grows, though it is likely that mysteries will always remain. The unexplored ocean is also a realm of beauty. Even without full knowledge, one can imagine the vastness of seafloor plains stretching in silence, the slow drifting of jellyfish glowing like lanterns, the forests of corals rising from dark seamounts, and the great rivers of current flowing endlessly in hidden circuits. It is a beauty both real and symbolic, representing the unknown that persists even in a world dominated by technology and data. The ocean holds secrets that resist easy revelation, a reminder that the Earth is larger, deeper, and more complex than human ambition can fully contain. To say that 95% of the ocean remains unexplored is, ultimately, to recognize that our planet still holds mysteries as profound as any beyond the stars. It is to admit that beneath the surface lies a vast world we barely know, a world that shapes our lives and sustains our breath. It is to be reminded that exploration is not finished, that discovery is still possible, and that wonder lies hidden in the depths. The ocean, dark and uncharted, waits like a library unopened, its volumes sealed but ready to reveal their stories to those willing to turn the pages. In that unexplored realm lies not only knowledge but also perspective, the understanding that the unknown is not something distant and alien, but something as close as the waves on a familiar shore. The ocean is incredibly biodiverse, a living expanse that harbors a richness of life more vast and varied than any other ecosystem on Earth. From the surface waters that shimmer with sunlight to the cold, lightless depths of the abyss, every layer of the sea is alive with organisms that have adapted to its conditions. It is difficult to grasp the sheer scale of this diversity, for the ocean covers the majority of the planet and penetrates to depths that seem almost limitless. Within it, countless species exist, many known to us, many more still undiscovered, each part of an intricate web that sustains the balance of life on Earth. At the most familiar level, the biodiversity of the ocean reveals itself in the creatures people recognize: whales breaching in cold northern seas, dolphins leaping through waves, sharks gliding with ancient grace, and colorful fish darting through coral reefs. These are the visible symbols of marine life, but they represent only a fraction of what exists beneath the surface. The ocean is home to microscopic phytoplankton, which drift in the sunlit layers, harnessing energy through photosynthesis and producing a significant portion of the oxygen that all terrestrial animals breathe. Zooplankton, tiny drifting animals, feed on these planktonic plants and in turn nourish larger creatures. This chain of life extends outward and upward, linking the smallest cells to the largest animals ever to live, such as the blue whale. The diversity of the ocean is not just a matter of species count but also of variety in form and adaptation. In coral reefs, for example, one can see a concentration of life unmatched anywhere else. These reefs, though covering only a small fraction of the ocean floor, are sometimes called the rainforests of the sea because of their density of species. Fish of every shape and color navigate labyrinths of coral branches, while invertebrates like sea stars, sponges, and anemones cling to the rocks. Predators, grazers, scavengers, and symbionts all coexist in these vibrant communities, relying on one another in delicate interdependencies. The reef is a living tapestry, woven from countless threads of evolution and survival strategies. Yet the ocean's biodiversity extends far beyond the warm, shallow reefs. In colder waters, kelp forests stretch upward from the sea floor, their fronds forming underwater canopies that shelter fish, sea otters, and crustaceans. In polar regions, life thrives under sheets of ice. Krill swarm in unimaginable numbers, supporting vast populations of whales, seals, and penguins. In the open ocean, where no shelter exists but the water itself, creatures have adapted to a life of constant movement. Schools of tuna race through the currents, while jellyfish drift with the flow, their gelatinous bodies pulsing rhythmically. Even in the deepest trenches, where sunlight never reaches and pressure is immense, strange forms of life endure: fish with bioluminescent lures, microbes that feed on chemical energy, and crustaceans that scavenge whatever drifts down from above. One of the most remarkable aspects of marine biodiversity is the ability of life to exploit even the harshest environments. Around hydrothermal vents on the ocean floor, where superheated water rich in minerals gushes from beneath the crust, ecosystems exist without any reliance on the sun. Instead, microbes use chemosynthesis, turning the chemicals in the vent fluids into energy. These microorganisms form the basis of entire communities that include giant tube worms, clams, and shrimp. Such adaptations demonstrate not only the resilience of life but also its creativity, finding ways to survive where it seems impossible. These discoveries have transformed our understanding of biology, suggesting that life might exist in similar conditions on other worlds. The ocean's biodiversity is also staggering in scale. Scientists estimate that there may be millions of species living in the sea, though only a fraction have been formally identified. Every expedition into the deep or study of a new reef tends to reveal organisms never before seen. The vastness of the ocean ensures that much of its life remains hidden, beyond the reach of nets, cameras, or submersibles. This hidden richness is a reminder that humanity's knowledge is incomplete, that the ocean holds secrets beyond our imagination. This biodiversity plays a crucial role in sustaining the balance of the planet. Marine organisms cycle nutrients, regulate the chemistry of the atmosphere, and stabilize ecosystems. The productivity of phytoplankton influences global carbon levels, drawing carbon dioxide from the air and sequestering it in the deep ocean when these organisms die and sink. Coral reefs protect coastlines from erosion by breaking waves, while mangrove forests and seagrass beds provide nurseries for fish that support human fisheries. The complexity of life in the ocean creates resilience, enabling ecosystems to recover from disturbances, but only up to a point. Humanity's relationship with ocean biodiversity has always been one of dependence. People rely on the sea for food, for livelihoods, and for cultural inspiration. The variety of fish and shellfish harvested from the ocean feeds billions of people, particularly in coastal regions. Beyond food, marine life has provided materials, medicines, and even models for technological innovation. The study of whale communication, the design of ships inspired by fish, and the development of drugs derived from marine sponges are just a few examples of how human ingenuity has drawn from the sea's abundance. The cultural and spiritual connections are equally deep, as communities across the world weave marine animals into myths, rituals, and traditions. Yet the richness of the ocean is not infinite, and in recent centuries it has come under increasing strain. Overfishing depletes populations faster than they can recover, reducing not only numbers but also genetic diversity. Coral reefs, those cradles of marine variety, are bleaching and dying as waters warm and acidify under the influence of climate change. Plastic pollution and oil spills threaten ecosystems at every level, from microscopic plankton that ingest tiny particles to whales that suffer entanglement and ingestion of debris. The loss of biodiversity in the ocean is not just the loss of species but the unraveling of complex systems upon which both marine and human life depend. The knowledge that the ocean is incredibly biodiverse carries with it both wonder and responsibility. To marvel at the endless adaptations, the colors, the forms, and the strategies of survival is to recognize the ingenuity of life itself. To understand that this diversity sustains the planet is to acknowledge our reliance on it. And to see that it is threatened is to be reminded of the urgency of protecting it. The ocean is not an infinite resource but a living system, its richness fragile despite its immensity. In contemplating the biodiversity of the ocean, one feels a mix of awe and humility. It is the stage upon which life first appeared on Earth, the cradle from which all terrestrial creatures ultimately descend. Its diversity is the record of billions of years of evolution, branching into forms as different as microscopic algae and massive whales. It is the unseen world that supports the visible one, the hidden abundance that makes the Earth habitable. To speak of the ocean as incredibly biodiverse is to speak of the essence of life itself, a reminder that beneath the waves lies the greatest collection of living wonders this planet has ever known. The longest mountain range on Earth is not one we can easily see. It does not cut across continents with snowy peaks or attract climbers eager to conquer summits. Instead, it lies hidden beneath the surface of the oceans, stretching across the globe in an almost continuous band of volcanic ridges. This underwater system, known as the mid-ocean ridge, is the greatest mountain chain on the planet, running more than 60,000 kilometers in length. Its sheer scale surpasses any land-based range, dwarfing the Andes, the Rockies, or the Himalayas. Yet, because it is concealed beneath the waves, it often escapes our imagination when we picture Earth's geography. To think of mountains is usually to think of towering peaks, rugged cliffs, and ranges that shape horizons. But beneath the ocean, the same processes that build mountains on land continue to operate on a grander scale. Along the mid-ocean ridge, tectonic plates pull apart, and molten rock from Earth's mantle rises to fill the gaps. As the magma cools, it solidifies into new crust, creating a ridge of volcanic mountains that extend across the seabed. This process is continuous, making the ridge not only the longest mountain range but also the most active site of geological construction on Earth. Every moment, new land is being born in the darkness of the ocean depths. The mid-ocean ridge system circles the planet like a seam on a baseball. It passes through the middle of the Atlantic, where it is known as the Mid-Atlantic Ridge, and continues into the Indian and Pacific Oceans, forming an interconnected network. The peaks of this underwater range often rise more than 2,000 meters above the ocean floor, and in some places, they break the surface to form islands. Iceland, for instance, is a visible part of this submerged chain, a place where the ridge emerges above the sea to create a landmass inhabited by people. But most of the system remains hidden far below the surface, where sunlight cannot penetrate. The scale of this mountain range changes how we view the Earth itself. It reveals that the planet's surface is not static but dynamic, constantly reshaped by the forces of plate tectonics. The longest mountain range is a physical record of the Earth's restless energy, a mark of the deep processes that drive continents to drift and oceans to open. When scientists mapped the ocean floor in detail during the 20th century, the discovery of this immense ridge was a revelation. It confirmed the theory of plate tectonics, showing that the seafloor was not ancient and unchanging but continually renewed along these volcanic seams. The presence of the mid-ocean ridge also creates unique environments. Along its length, fissures in the Earth's crust allow seawater to seep down, where it is heated by magma before being expelled back into the ocean through hydrothermal vents. These vents release water rich in minerals and metals, creating plumes that sustain extraordinary ecosystems. In the pitch-black depths, where sunlight cannot support photosynthesis, life has found another way. Microbes harness the chemical energy of the vent fluids, forming the base of a food web that includes giant tube worms, blind shrimp, and other creatures adapted to the extreme conditions. These ecosystems show that life can thrive without sunlight, relying instead on the chemistry of the Earth itself, and they suggest possibilities for life in other parts of the universe, on icy moons with hidden oceans. The sheer length of the mid-ocean ridge invites comparison with land-based ranges. The Andes, the longest continental range, stretch nearly 7,000 kilometers, a mere fraction of the underwater chain's 60,000. The Himalayas, with their towering peaks such as Mount Everest, may claim the title of the highest mountains, but in terms of continuity and scale, they are small beside the oceanic range. What makes the mid-ocean ridge so extraordinary is not just its length but its global reach, forming a nearly unbroken circuit around the planet. Despite its immensity, the ridge is largely invisible to everyday human life. Covered by kilometers of seawater, it exists in a realm that is rarely visited and only partially explored. Submersibles and remotely operated vehicles have revealed glimpses of its ridges, rifts, and vent fields, but vast stretches remain unseen. This hidden nature gives the ridge an aura of mystery, reminding us how much of Earth remains beyond our direct experience. It is as if the planet has concealed its greatest feature beneath the oceans, allowing only fragments to surface as islands. The existence of such a vast underwater mountain range also alters our sense of proportion. It suggests that the features we are most familiar with on land are only part of the story. The true geography of Earth includes landscapes more immense and alien than those we can see. To grasp that the longest mountain range lies beneath the sea is to accept that human perspective is limited, framed by what is visible and accessible. The mid-ocean ridge challenges that perspective, expanding our understanding of Earth as a planet shaped as much by hidden forces as by those evident in daylight. The ridge also influences the broader environment of the oceans. The upwelling of magma and the creation of new crust push apart the seafloor, shaping the size and position of ocean basins. This movement, in turn, affects sea levels, circulation patterns, and the distribution of marine ecosystems. The physical form of the Earth's surface is continually adjusted by the slow but relentless activity of the ridge. Over millions of years, continents drift across the globe, carried along by the conveyor belts of new crust that spread outward from these underwater mountains. The story of the ridge is, in many ways, the story of the planet's surface in motion. For humanity, the mid-ocean ridge has practical as well as scientific significance. The minerals and metals released at hydrothermal vents attract interest as potential resources. Cobalt, copper, and rare earth elements deposit around vent fields, and in the future, deep-sea mining may target these materials. At the same time, the ridge holds clues to hazards such as earthquakes and volcanic eruptions, since the movement of tectonic plates along its length generates seismic activity. Understanding the dynamics of the ridge helps scientists predict and interpret such events, offering insights into the forces that occasionally shake the continents. Yet perhaps the most striking aspect of the mid-ocean ridge is how it underscores Earth's uniqueness. No other known planet in the solar system has a comparable feature, a globe-spanning range driven by plate tectonics. The ridge is a fingerprint of Earth's living geology, evidence that this planet is still shaping itself from within. To imagine the mid-ocean ridge is to picture a world alive with movement, its skin constantly renewed by fire and water. It is a reminder that the ground beneath us, though seemingly solid, is part of a vast, shifting system tied together by forces deep within the mantle. The fact that the longest mountain range on Earth lies underwater is a testament to the hidden wonders of the planet. It challenges the assumptions formed by our land-based experience and reveals a world far more immense and dynamic than we might otherwise believe. The ridge is not a landscape we can easily visit, but it is one that shapes the earth beneath our feet and the seas that surround us. It is both ancient and ever new, the place where continents are born, oceans are reshaped, and life finds unexpected footholds. Though it lies out of sight, the mid-ocean ridge is central to the character of the planet, the unseen backbone of Earth's geography. The biggest waterfall on Earth is not found tumbling over cliffs on land but hidden beneath the surface of the ocean, a paradox that captures the strangeness and wonder of the deep. When people imagine waterfalls, they think of roaring cascades like Angel Falls in Venezuela, Niagara straddling the border of the United States and Canada, or Victoria Falls in Africa, where walls of water crash with thundering force. These are awe-inspiring spectacles, yet none of them comes close in scale to the immense flow that occurs in silence, unseen beneath the waters of the North Atlantic. Known as the Denmark Strait Cataract, this underwater waterfall lies between Greenland and Iceland, where cold, dense water from the Arctic meets warmer, lighter water from the Atlantic. The result is the largest waterfall on the planet, plunging more than 3,500 meters, far surpassing any cascade on land. The existence of such a phenomenon might sound contradictory. How can a waterfall exist beneath the ocean, where everything is already water? The key lies in density. Just as oil floats on water because it is lighter, warm, salty water behaves differently from cold, dense water. Where these two bodies of water meet, the denser water sinks beneath the lighter one, creating a downward flow that resembles a waterfall on a massive scale. In the Denmark Strait, this happens on an epic level. Cold Arctic water, heavier and denser, pours southward into the Atlantic, cascading downward in a plunge that makes Niagara or Angel Falls seem like small streams by comparison. The volume of water moving here is estimated at more than 5 million cubic meters per second, about 20 times the flow of all the rivers in the world combined. Unlike waterfalls on land, this one is invisible to the human eye. The Denmark Strait is covered by a surface of churning waves and icy winds, with no obvious sign of the torrent below. The drama unfolds in silence, without mist or thunder, hidden in the deep currents that shape the ocean. For centuries it went unnoticed, unknown even to sailors who braved those treacherous waters. Only with modern oceanography, using instruments that measure temperature, salinity, and currents, did scientists uncover the existence of this immense underwater cascade. In its invisibility lies part of its wonder, a reminder that the Earth holds marvels that defy expectations, hiding spectacles where they are least expected. This underwater waterfall is not just a curiosity but a vital part of the planet's systems. It is one of the engines that drives the global circulation of the oceans, often described as the conveyor belt of water that redistributes heat, nutrients, and gases around the world. The sinking of cold, dense water in the Denmark Strait helps pull warm currents northward, such as the Gulf Stream, which carries tropical warmth into the North Atlantic and moderates the climate of Europe. Without the continuous plunge of this underwater waterfall, the circulation of the oceans would weaken, and climates across continents would change dramatically. Thus, hidden in the cold and darkness, this invisible cascade plays a role in shaping weather, seasons, and the habitability of distant lands. The scale of this waterfall is almost beyond comprehension. Angel Falls, the tallest waterfall on land, drops about 979 meters. The Denmark Strait Cataract plunges more than 3,500 meters, over 3 times as far. Victoria Falls is sometimes called the largest by volume, with around 1,000 cubic meters per second tumbling over its edge. The underwater cataract dwarfs that figure with millions of cubic meters per second. And yet, despite its immensity, it leaves no roaring echo, no mist rising into the sky, no visible spectacle for the human eye. Its greatness is hidden, known only through measurements and imagination. The very existence of an underwater waterfall invites reflection on how little we know of the ocean. More than 90% of it remains unexplored, and phenomena like the Denmark Strait Cataract are reminders of how much remains unseen. The idea that the greatest waterfall in the world exists beneath the surface, unnoticed until recent decades, humbles the human sense of mastery over nature. It suggests that Earth still holds secrets, that discovery is still possible even in an age of satellites and global communication. The ocean keeps its mysteries not out of malice but by its very nature, vast, dark, and difficult to penetrate. This hidden cascade also invites metaphor. It is a waterfall without roar, without witness, a silent power that works invisibly yet sustains the world. In this sense, it resembles many of the processes of nature: oxygen produced by plankton drifting unseen, currents moving heat across the planet, or the slow drift of tectonic plates shaping mountains and valleys. Much of what makes life possible happens beyond the realm of human senses, in places we cannot easily see or hear. The Denmark Strait Cataract is a symbol of that hidden power, a reminder that nature does not exist only for spectacle but also for function, its grandeur often invisible. For those who study the oceans, the underwater waterfall offers both challenge and opportunity. Measuring it requires instruments that can withstand the harsh environment of the North Atlantic, where storms lash the surface and icy waters resist intrusion. Scientists lower sensors into the depths, deploy moored equipment that records currents over months, and use satellites to infer patterns from above. Each measurement adds to an understanding of how this invisible cascade works, how stable it is, and how it might change in response to global warming. If Arctic waters grow fresher due to melting ice, their density will decrease, potentially weakening the waterfall. Such a change could slow the global conveyor belt of circulation, altering climates far beyond the North Atlantic. Thus, the fate of this hidden cascade is tied to the fate of the world. Yet beyond science and climate, there is something deeply poetic in knowing that the largest waterfall on Earth exists beneath the waves. It shifts the imagination, asking us to see the ocean not as a flat expanse but as a world of vertical drama, of hidden cliffs and plunges, of movements as dynamic as any mountain or canyon on land. The sea conceals mountains taller than Everest, trenches deeper than any canyon, and now waterfalls greater than any above water. To think of it this way is to see the ocean not as a void but as a landscape in motion, a place of grandeur equal to any on land, though cloaked in silence and darkness. The Denmark Strait Cataract, then, is not only a scientific fact but a reminder of perspective. It tells us that size and spectacle are not always visible, that greatness can exist without being seen, and that the workings of the planet extend far beyond the limits of our senses. To know that beneath the cold waters of the North Atlantic, millions of tons of water plunge thousands of meters in a ceaseless fall, is to gain a deeper respect for the hidden structures of Earth. It is to realize that the planet's most extraordinary features may not be those that shout their presence with thunder and mist, but those that whisper in silence beneath the waves, shaping the world in ways we can scarcely imagine. The ocean influences and regulates Earth's climate, acting like the planet's heart, pulsing with currents and distributing heat and energy across the globe. Without it, the climate would not be stable, and life as we know it could not endure. Just as the heart pumps blood to sustain the body, the ocean circulates water, heat, and nutrients, maintaining a balance that reaches into every corner of the Earth. It is vast, covering most of the planet, and within its depths lies the power to moderate temperatures, generate weather patterns, and shape the seasons. Its role is often hidden from view, but its influence is present in every drop of rain, every gentle breeze, and every storm that sweeps the land. The ocean acts as an enormous reservoir of heat. Water has a remarkable capacity to store energy, absorbing sunlight during the day and releasing it slowly over time. Because of this, the ocean prevents extreme fluctuations in temperature that would otherwise make much of the Earth uninhabitable. Coastal regions, for example, are tempered by the nearby sea. Summers are cooler and winters are milder compared to inland areas at the same latitude. This moderating effect exists because the ocean functions as a buffer, holding on to heat when the sun is strong and giving it back when the air grows cold. The cycle of absorption and release is continuous, a silent rhythm that parallels the steady beat of a heart. Currents within the ocean amplify this role, carrying warmth from one part of the globe to another. The Gulf Stream, perhaps the most famous of these currents, transports warm water from the tropics across the Atlantic toward Europe. Without it, much of northern Europe would experience harsher, more frigid winters. Similarly, currents in the Pacific and Indian Oceans redistribute heat, balancing temperatures between equatorial and polar regions. This global circulation system, often called the conveyor belt of the ocean, is driven by differences in temperature and salinity, creating a deep flow of water that loops around the planet. It is through this circulation that the ocean regulates not only local climates but also the overall stability of Earth's climate system. Beyond heat transport, the ocean influences the atmosphere in direct and visible ways. The evaporation of seawater feeds clouds and weather systems, generating rainfall that nourishes forests, fields, and rivers. Entire monsoon patterns, which sustain agriculture for billions of people, depend on the interaction between the ocean's surface and the atmosphere. El Niño and La Niña, recurring climate phenomena linked to changes in Pacific Ocean temperatures, cause shifts in rainfall, drought, storms, and even fisheries around the world. These events illustrate how the ocean is not merely a backdrop but an active player, sending ripples of change through the air above and the lands beyond. The ocean also plays a central role in regulating greenhouse gases, particularly carbon dioxide. Phytoplankton, those tiny drifting organisms that photosynthesize in the upper layers, draw in carbon dioxide from the air and release oxygen. Much of this carbon becomes trapped in the ocean, either dissolved in the water or carried to the depths when organisms die and sink. This process, known as the biological pump, makes the ocean the largest carbon sink on Earth, absorbing a significant portion of the carbon dioxide emitted by human activity. By storing this greenhouse gas, the ocean slows the pace of global warming, though at the cost of increased acidification of its waters. Like the heart filtering blood, the ocean filters the atmosphere, cleaning it in ways we barely notice until disruption occurs. When thinking of the ocean as the planet's heart, one can imagine the tides as pulses, the currents as arteries, and the exchange of gases and heat as lifeblood flowing through the system. Every storm, every gentle drizzle, every seasonal cycle is tied to this beating heart. Without it, the atmosphere would be unstable, and the delicate balance that makes Earth habitable would collapse. Even deserts, seemingly disconnected from the sea, are shaped by its influence. The air that carries dryness across continents once gathered moisture from the ocean. The pattern of winds that sweeps across sands is driven by differences in heat between land and sea. The ocean touches every climate zone, even those farthest from its shores. The deep ocean, cold and dark, also plays its part in this regulation. Waters that sink near the poles carry oxygen and nutrients downward, storing heat and gases for centuries before slowly rising again in distant parts of the world. This cycle links past and future, present and distant places, binding the climate together in a continuous system. It is a reminder that the ocean's influence is not limited to immediate weather but extends to long-term climate stability. The great ice ages and warming periods of Earth's history have all been tied in some way to the ocean's rhythms, its slow and powerful breathing that shapes epochs. Humanity depends on this regulation more than it often realizes. Cities along coasts are built in climates softened by the sea, agriculture thrives in rainfall sustained by ocean evaporation, and economies rely on predictable seasons made possible by currents and circulation. Yet this dependence also makes humanity vulnerable when the system is disturbed. As the climate warms due to greenhouse gas emissions, the ocean absorbs not only more heat but also more carbon. This leads to rising sea levels, disrupted currents, and more extreme weather events. Hurricanes intensify as warmer waters fuel their strength, while melting ice at the poles threatens to alter circulation patterns that have remained steady for millennia. The beating heart of the planet is under stress, and its irregular rhythms manifest as crises felt across the globe. Still, the ocean retains its resilience. Like the heart of a living being, it continues its work regardless of whether it is acknowledged. Waves crash, currents flow, and tides rise and fall in ceaseless cycles. The ocean does not cease to regulate climate simply because it is ignored, but its capacity is not infinite. There is a limit to how much heat and carbon it can absorb without consequence. Just as strain upon the human heart leads to illness, strain upon the ocean leads to imbalance. The floods, droughts, storms, and rising seas of our age are signs of a heart under duress. To imagine the ocean as Earth's heart is also to see the planet as a living system, where air, land, and water are not separate domains but organs of a single body. The forests may be its lungs, the soil its skin, but the ocean is the beating center, circulating energy and balance. In every raindrop, in every gentle breeze, in the warmth of a temperate winter or the relief of a cool summer day, the pulse of the ocean can be felt. Humanity's fate is intertwined with this rhythm, as dependent on it as a body is on the steady beat within its chest. In recognizing the ocean's role as the planet's heart, one gains not only scientific understanding but also a sense of humility. The sea is vast, powerful, and essential, but it is not invulnerable. It has carried the climate of Earth through ages of ice and warmth, sustaining life through upheavals and extinctions, yet now it faces pressures born of human activity. Whether the heart of the planet continues to beat with strength or falters under strain depends on the choices humanity makes. To honor the ocean is to honor the balance of Earth itself, to care for the rhythm that sustains every living breath. Sea water contains about 3.5% salt, a simple measurement that holds within it the history of the Earth, the workings of its chemistry, and the conditions of life that have developed across billions of years. To the casual observer, the ocean appears as a vast expanse of blue, restless in motion, sometimes calm and sometimes raging with storms. But within each drop lies a composition shaped by eons, an intricate mixture of water and dissolved minerals, with salt being the most abundant. That figure, 3.5%, may seem modest, but when multiplied by the scale of the sea, it amounts to an almost unimaginable quantity of salt, trillions of tons spread throughout the oceans, enough to coat the planet in layers far deeper than any mountain range. The salt of the sea is primarily sodium chloride, the same compound we sprinkle on food, yet in the ocean it is part of a much larger chemical balance. Alongside sodium and chloride ions are magnesium, calcium, potassium, sulfate, and trace elements such as iodine and iron. Together they form the mineral richness of seawater, giving it the taste so distinctive that a sip of ocean water can never be mistaken for anything else. The 3.5% concentration is not just a flavor but a defining characteristic of the marine environment. It dictates the way organisms evolve, how they regulate their bodies, and how ecosystems function. The presence of salt in the ocean traces back to the Earth's earliest days. When the planet was young, rain fell for millions of years, weathering rocks on the land and carrying dissolved minerals into rivers that emptied into the seas. Volcanic activity released gases and minerals as well, adding to the mixture. Over time, the oceans became a vast basin where these substances accumulated, for unlike rivers or lakes, the sea has no outlet beyond evaporation. When water rises into the atmosphere as vapor, the salts remain behind, gradually concentrating the oceans into their present salinity. The figure of 3.5% is the result of this long, patient process, shaped by geology, weather, and chemistry acting together. That salinity is not uniform everywhere. It varies slightly depending on location, climate, and depth. In regions of heavy rainfall or where large rivers pour freshwater into the sea, such as near the mouths of the Amazon or Ganges, the salt concentration decreases. In contrast, in enclosed seas where evaporation is intense, such as the Red Sea or the Persian Gulf, salinity rises above average, sometimes exceeding 4%. The Dead Sea, technically a salt lake rather than a true ocean basin, is even more extreme, with salinity more than 8 times the global average, so dense that swimmers can float effortlessly on its surface. Yet despite these local differences, the open oceans remain remarkably stable at about 3.5%, a consistency that has endured for millions of years. Life in the ocean is built around this salinity. Marine organisms have evolved intricate ways to cope with the constant presence of salt. Fish, for example, must regulate the balance of salts and water in their bodies through specialized organs in their gills and kidneys. Some species drink seawater and excrete the excess salts, while others have adapted to thrive in brackish or variable environments. Corals and shell-building organisms rely on the availability of calcium and carbonate ions in seawater to form their structures. Even microorganisms, which may seem indifferent to chemistry, are finely tuned to the salt balance of their surroundings. The entire architecture of marine life depends on the stability of that 3.5%. For humans, the saltiness of the sea has always been a fact both practical and symbolic. Salt has been harvested from seawater for thousands of years, often through the simple method of evaporation in shallow pools. Civilizations valued salt as a preservative, a seasoning, and a commodity so precious it shaped economies and trade routes. Even today, much of the salt used around the world comes from the ocean, crystallized in sunlit pans where water leaves and minerals remain. The ocean has thus been both a giver of life and a source of sustenance, not only through its fish and resources but also through its very chemical composition. The salt in the ocean also influences its physical behavior. Salinity, combined with temperature, determines the density of seawater, which in turn drives currents and circulation patterns. When water becomes salter through evaporation or the formation of sea ice, it grows denser and sinks, creating deep currents that flow across basins. These movements are part of the global conveyor belt of the ocean, transporting heat, nutrients, and gases around the world. The presence of 3.5% salt is not just a chemical fact but a driver of climate and weather, linking the chemistry of the sea to the air above and the land beyond. There is a paradox in seawater's salinity. It is essential for marine life and for the stability of Earth systems, yet it makes the ocean undrinkable to humans. To consume seawater in significant amounts is to court dehydration, as the body must expend more water to rid itself of the excess salt than it gains from drinking. Thus the very abundance of water in the ocean cannot directly satisfy thirst, a reminder of the delicate balance between human needs and the conditions of the natural world. For people lost at sea, this truth becomes immediate and cruel, surrounded by water yet unable to drink. Despite being so familiar, the saltiness of the ocean is also a reminder of how much remains unknown. Scientists study the variations in salinity to understand climate change, as shifts in rainfall, evaporation, and melting ice alter the balance. In the Arctic, freshwater from melting glaciers dilutes the ocean, threatening to disrupt circulation patterns. In subtropical regions, evaporation intensifies, raising salinity in some areas. These changes are not mere numbers on charts but signals of deeper transformations in Earth systems. To measure salinity is to read the pulse of the planet, with that 3.5% figure serving as a baseline for detecting shifts that could reshape the climate and ecosystems alike. Beyond science, the saltiness of the sea has entered human imagination. It is part of the symbolism of the ocean as a place of eternity and memory, where the taste of salt recalls both tears and sweat, labor and sorrow. Writers and poets have long associated the flavor of the sea with human emotion, tying chemistry to metaphor. The fact that every drop contains salt links the ocean to the human body itself, for our blood holds a salinity not far from that of seawater, echoing the ancient kinship between life and the sea from which it emerged. To say that seawater contains about 3.5% salt is therefore to speak not only of chemistry but of history, life, and meaning. It is to recognize the slow accumulation of minerals over eons, the adaptation of creatures to a saline world, the shaping of climate by density and currents, and the role of salt in human culture. That small percentage, measured with precision, reflects the vastness of Earth's processes, linking rocks, rivers, volcanoes, and life itself. It is a simple fact with endless implications, a reminder that even the most familiar qualities of the world carry depths of mystery and significance. The Pacific Ocean, vast and immeasurable to the human eye, stretches across nearly 1/3 of the Earth's surface, covering an area so immense that it defies ordinary comprehension. It is the largest ocean on our planet, a body of water so wide and deep that it seems to form a world of its own. When one says that it covers around 30% of Earth's surface, the figure alone is staggering, but numbers cannot fully capture its immensity. This ocean is larger than all the land masses of Earth combined, spreading over more than 63 million square miles, a living testament to the boundless scale of nature. Its waters link continents, cradle islands, and shape climates, and its depths hide some of the planet's greatest mysteries. Standing at the shore of the Pacific, one can hardly imagine the distances that unfold beyond the horizon. To the west lie the coasts of Asia and Australia, to the east the long stretches of the Americas. Between them spreads an expanse so wide that early explorers took months to cross it, often perishing before sighting land. The ocean reaches nearly 19,000 kilometers from Panama to the Philippines and stretches about 15,000 kilometers from north to south, from the icy edge of the Arctic all the way down to the freezing waters of Antarctica. It is a blue dominion that dwarfs everything, shaping both human history and the planet's rhythms. The Pacific Ocean's immensity carries with it extraordinary power. Its sheer size influences the Earth's climate in profound ways. The trade winds that sweep across its surface, the currents that circulate through its depths, and the phenomena that arise from its waters, such as El Niño and La Niña, can bring droughts, floods, storms, and shifts in temperature to lands thousands of miles away. Its ability to store and distribute heat makes it a global regulator, a stabilizer of sorts, without which the balance of climates across continents would be far different. The Pacific is not only vast in space but also in influence, a hidden architect of weather and life across the world. It is also a place of immense depth. While its surface stretches farther than the imagination can easily picture, beneath lies another realm, descending into the abyss. The Pacific is home to the Mariana Trench, the deepest place in the ocean, where the seafloor plunges nearly 11 kilometers below sea level. Scattered across its floor are mountain ranges larger than those on land, volcanoes taller than Everest when measured from their base beneath the waves, and countless seamounts that remain unmapped and unexplored. The ocean is not a flat plain but a rugged, dynamic world of ridges, trenches, and valleys, hidden beneath miles of water. Its surface, however, tells another story. Dotting the Pacific are tens of thousands of islands, from the volcanic peaks of Hawaii to the coral atolls of the Marshall Islands, from the rainforests of Papua New Guinea to the ancient cultural landscapes of Polynesia. These islands, though small compared to the vast ocean, have been homes, sanctuaries, and stepping stones for human civilization. Long before Europeans dared to venture across its waters, the Pacific was crossed by Polynesian navigators, who read the stars, the waves, and the flight of birds to guide them across seemingly endless horizons. Their voyages connected far-flung islands into cultural webs, proving that even the largest ocean could be bridged by skill, courage, and imagination. The Pacific Ocean has always been central to human history. For millennia, it provided food, from its abundant fish to its whales and shellfish, sustaining entire communities. It shaped myths, giving rise to gods and legends tied to its moods and storms. Later, it became the stage for great voyages of discovery. Spanish galleons crossed it to link the Americas with Asia, trading silver for silk and spices. Captain James Cook charted vast stretches of it in the 18th century, adding new islands and coastlines to maps of the known world. In the 20th century, it became the theater of fierce battles during the Second World War, its islands and waters central to strategies and sacrifices. Today, it remains a highway of commerce, with shipping lanes that carry goods and resources vital to modern life. But the Pacific is not only a theater for human action. It is also a world of extraordinary biodiversity. Its waters teem with countless species, from the great blue whale to the smallest plankton. Coral reefs flourish in its warmer regions, hosting ecosystems as rich as any rainforest. Schools of tuna, pods of dolphins, and flocks of seabirds depend on its abundance. Beneath its surface, strange creatures thrive in the cold, dark depths, where hydrothermal vents spew mineral-rich water that sustains entire communities of life, independent of sunlight. The Pacific, vast and varied, is both a cradle and a sanctuary of life, offering habitats across a spectrum of conditions unmatched by any other part of the Earth. Yet, for all its immensity, the Pacific is not immune to human touch. Its currents carry plastic waste to form gyres of floating debris, its coral reefs are threatened by rising temperatures and acidifying waters, and its fisheries are under pressure from overexploitation. Even in its most remote reaches, scientists have found traces of human activity, from microplastics in the stomachs of deep-sea creatures to chemical pollutants embedded in sediments. The Pacific's enormity might seem to place it beyond harm, but in reality, its vastness only spreads the evidence of human influence further, making the challenge of preservation greater. There is a paradox in the Pacific Ocean's relationship with humanity. On the one hand, it represents boundlessness, a realm of freedom and possibility. On the other, it reveals our limits, reminding us of how small we are in the face of such magnitude. Standing on its shore, one feels both humbled and inspired, caught between awe at its scale and recognition of its fragility. It is a mirror of Earth itself, immense, life-giving, but finite and vulnerable. To say that the Pacific covers 30% of Earth's surface is to state a fact, but beneath that fact lies a story. It is the story of a blue expanse that shapes the world's weather, nurtures its creatures, and has been both a barrier and a bridge for human beings. It is the story of an ocean that hides mountains, valleys, and worlds unseen, while on its surface, it has carried canoes, galleons, steamships, and modern vessels across its face. It is the story of abundance and mystery, of danger and opportunity, of a place that seems eternal but bears the marks of change. The Pacific Ocean, in its scale, cannot be fully contained in any number, map, or description. To look upon it is to glimpse the infinite, to feel the Earth's vastness pressed into a single horizon. It is the largest ocean, yes, but more than that, it is the Earth's defining feature, the great expanse that connects continents, that sustains life, and that humbles us with its power. Its waves carry the whispers of history, its depths guard secrets yet undiscovered, and its immensity reminds us always of how much remains unknown. In contemplating the Pacific, we are reminded that our planet is, above all, a blue world, and that the ocean's presence defines not only the Earth itself but also the destiny of those who live upon it. Beneath the rolling blue surface of the Pacific Ocean lies a world so hidden and profound that it challenges the very limits of human understanding. The Mariana Trench, the deepest part of the world's oceans, exists like a scar across the Earth's crust, an immense underwater canyon that has both fascinated and intimidated scientists, explorers, and dreamers alike. It is a place where the planet folds into itself, where light never reaches, and where the weight of the water above creates pressure so immense that it seems nothing could survive. Yet it is also a realm where life endures, where discovery continues to astonish us, and where the story of Earth itself is written in silence and darkness. The trench is situated in the western Pacific, east of the Philippines and just to the east of the Mariana Islands, which lend it their name. Stretching over 1,500 miles in length, the trench arcs like a great crescent, as though someone had pressed a finger deep into the ocean floor and left a permanent indentation. Its width varies, but in some regions, it spans over 40 miles. At its deepest known point, the Challenger Deep, the seafloor plunges nearly 36,000 feet beneath the surface, more than 10,900 meters. To grasp the magnitude of such depth, imagine the tallest mountain on Earth, Mount Everest, placed upside down into the trench. Even then, its peak would still lie over a mile beneath the water's surface. It is a measurement so staggering that the mind struggles to picture it, and words like deepest or lowest seem pale compared to the immensity of what they describe. The trench's origin lies in the restless geology of our planet. Earth's surface is broken into tectonic plates, massive slabs of rock that drift slowly across the mantle. At the site of the Mariana Trench, the Pacific Plate is forced beneath the smaller Mariana Plate in a process called subduction. The seafloor bends and plunges downward, sinking into the Earth's mantle, creating this immense chasm. This same process generates intense volcanic activity and forms the arc of islands nearby, reminding us that the trench is not just an inert feature but part of a dynamic system. It is a place where the Earth's outer skin is constantly consumed and renewed, where the story of continents, oceans, and mountains begins and ends in an endless cycle of change. Conditions at the bottom of the trench are unlike anywhere else on Earth. The pressure there is over 1,000 times greater than at the surface. For comparison, if a person were to descend without protection, their body would be crushed instantly by the sheer weight of the water pressing down. Temperatures hover just above freezing, and absolute darkness dominates the landscape. The only light is bioluminescence, emitted by organisms that have adapted to this eternal night. It is an environment hostile to most forms of life, yet remarkably, creatures survive and even thrive. Scientists have discovered strange amphipods, snailfish with transparent bodies, and microbial communities that live on chemical energy rather than sunlight. These organisms exist in slow, delicate balance, their very survival testimony to life's adaptability. For centuries, the trench was unknown to humankind. Its existence began to emerge during the great age of ocean exploration in the 19th century. The voyage of the HMS Challenger between 1872 and 1876 marked one of the first systematic attempts to measure ocean depths. By lowering weighted lines, the expedition revealed staggering measurements, identifying what would later be known as the Challenger Deep. That name has endured, paying tribute to the pioneering spirit of exploration that first dared to probe the unseen abyss. It was not until 1960, however, that humans themselves ventured into the trench. Jacques Picard, a Swiss oceanographer, and Don Walsh, a U.S. Navy lieutenant, descended in the bathyscaphe Trieste. This strange-looking vessel, resembling a massive steel ball attached to floats, was designed to withstand the crushing pressures of the deep. Their journey lasted nearly 5 hours as they sank slowly into the blackness. At the bottom, they remained for about 20 minutes. Their view limited by the clouds of sediment stirred by their arrival. Yet even in those fleeting moments, they reported seeing life, small fish and shrimp-like creatures, proof that the deepest part of the ocean was not barren, but alive. Their successful descent was hailed as a triumph of engineering and human courage, a bold venture into Earth's most inaccessible frontier. For decades after, no human returned to such depths. The trench remained largely a mystery, glimpsed only through occasional robotic probes and sonar mapping. Then, in 2012, filmmaker and explorer James Cameron made a historic solo dive to the Challenger Deep in the Deep-Sea Challenger, a submersible built to endure the crushing environment. He became the first person to reach the trench alone, spending hours at the bottom, filming, and collecting samples. His journey brought renewed attention to the trench, reminding the world of the wonders still hidden within our planet. More recently, other explorers and scientific teams have followed, each visit revealing more about the strange ecosystems and geology that thrive in this forbidding place. Despite these efforts, the Mariana Trench remains far less understood than outer space. More people have walked on the moon than have visited its floor. The sheer difficulty and expense of deep-sea exploration mean that most of the trench remains unseen, its mysteries intact. Sonar maps give us outlines, robotic dives collect samples, but the full richness of its ecosystem and the geological processes at work are still largely hidden. It is a reminder that even on our own planet, vast territories remain unexplored, waiting for the tools and determination to unlock them. Yet the trench is not merely a natural wonder. It is also a mirror reflecting humanity's impact on the planet. Recent studies have found traces of industrial chemicals and microplastics even at its greatest depths. The realization that human pollution has reached even this most remote environment is sobering. It suggests that no corner of Earth remains untouched by our activities. The Mariana Trench, which should symbolize the untouched extremes of nature, now bears silent witness to the global reach of our species. There is something profoundly humbling in contemplating the trench. It is a realm that does not belong to us, one that resists entry, demanding respect, ingenuity, and courage from those who attempt to visit. It dwarfs human scale, reminding us of our fragility in the face of nature's immensity. Yet it also calls to our curiosity, our relentless desire to explore and to know. The trench embodies both the limits of human survival and the boundless potential of human imagination. To think of the Mariana Trench is to think of silence, darkness, and pressure, but also of resilience, endurance, and discovery. It is a paradoxical place, hostile yet nurturing, remote yet connected, timeless yet constantly changing. It is the deepest point of the ocean, but also a reminder of the highest capacities of human courage and wonder. The Mariana Trench will continue to stand as one of Earth's most mysterious frontiers, a hidden cathedral of the deep where the story of the planet and the story of life intersect. It is not just a geographical fact but a symbol of how much remains to be discovered, how vast the unknown still is, and how small we are in the face of it. And yet, in that very smallness lies the beauty of our species, the will to keep reaching, to keep asking, to keep descending into the unknown in search of understanding. The oceans are often called the beating heart of the planet, and in many ways, this is true. They regulate climate, drive weather systems, sustain life, and connect distant lands through vast currents that never cease their motion. Yet one of their most remarkable roles is less visible, hidden in the balance of temperatures and energies that govern Earth's systems. The oceans absorb around 90% of the excess heat generated by human activities, especially the burning of fossil fuels and the release of greenhouse gases into the atmosphere. This fact, simple in its phrasing, contains profound meaning for life on Earth. It tells of the resilience of the oceans, their capacity to shield humanity from the full force of climate change, and also of their vulnerability, for this heat absorption comes at a cost that is beginning to unfold before our eyes. To understand this, one must imagine the Earth as a delicate system of balances. Energy from the sun reaches our planet every day, warming land, air, and sea. In a natural state, much of this energy is radiated back into space, keeping the planet's temperature relatively stable. But with the increase of greenhouse gases such as carbon dioxide and methane, more of this heat becomes trapped within the atmosphere, creating an imbalance. The Earth, unable to release heat as quickly as it gains it, begins to warm. Yet the atmosphere alone is thin and incapable of holding vast amounts of energy. Instead, the oceans act as reservoirs, absorbing most of this excess heat and distributing it through their waters. Without this ability, the average temperature on land would have risen far more dramatically, and the planet's climate would already be unrecognizably hostile. The scale of this absorption is staggering. Since the mid-20th century, scientists estimate that more than 90% of the energy trapped by greenhouse gases has been taken in by the oceans. This means that only a small fraction remains in the air and on the land surface, which explains why atmospheric warming, though significant, has not been as extreme as it might otherwise have been. The oceans, vast and deep, are like a great sponge, soaking up the heat of human industry. The top few hundred meters, stirred by winds and waves, are the first to absorb and distribute this energy, but over time the heat penetrates deeper, altering currents, disrupting ecosystems, and reshaping the chemistry of the seas. One must not mistake this absorption for a benign process. It is not as though the oceans can take in heat endlessly without consequence. Already, signs of strain are evident. As ocean waters warm, they expand, contributing to rising sea levels that threaten coastlines and low-lying nations. Warmer water also disrupts marine ecosystems. Coral reefs, for example, are extraordinarily sensitive to changes in temperature. When the seas grow too warm, corals expel the symbiotic algae that nourish them, leading to bleaching events that leave entire reefs ghostly white and vulnerable to death. These reefs, often called the rainforests of the sea, support immense biodiversity and provide food and protection for millions of people. Their decline is one of the starkest signals of the ocean's burden. Marine life beyond the reefs is also deeply affected. Fish migrate to cooler waters, disrupting traditional patterns of fishing and endangering communities that rely on them. Species adapted to narrow temperature ranges struggle to survive, while invasive species expand their reach. The intricate balance of food chains begins to shift, with consequences that ripple from the smallest plankton to the largest whales. Even the great ocean currents, such as the Gulf Stream and the Pacific's trade wind-driven circulations, are vulnerable. These currents are driven by differences in temperature and salinity, and as warming alters those factors, the circulation of heat around the globe may weaken or change, affecting weather systems on distant continents. The human consequences of this are already being felt. Stronger and more frequent storms, intensified by the additional energy in the atmosphere and the ocean, batter coastlines and flood cities. Heat waves in the sea, once rare, now strike with alarming regularity, devastating ecosystems and fisheries. Rising sea levels threaten millions of people living in coastal regions, from small island nations to sprawling megacities. The very act of the oceans shielding humanity from worse warming has, paradoxically, created new vulnerabilities that grow with every year of continued emissions. Yet, alongside these challenges, there is also something profoundly humbling in the ocean's capacity. To realize that the seas have absorbed 90% of the heat is to recognize how intertwined life on Earth is with the rhythms of the ocean. Every breath of air, every meal drawn from the sea, every breeze that cools a summer's day is touched by the hidden work of these waters. The oceans have acted as guardians, buying humanity time to respond to the crisis we have created. But they are not infinite in their endurance. As they warm, their ability to continue absorbing heat diminishes, leaving more energy in the atmosphere and accelerating the pace of change. This moment in history is thus a fragile one. The oceans have shielded us for decades, but the consequences of their burden are rising to the surface. They cannot be endlessly forgiving, and their silent warning is becoming louder in the form of bleaching reefs, shifting currents, stronger storms, and melting ice caps. To acknowledge that they absorb 90% of excess heat is not just to marvel at a statistic but to confront a truth about our place on the planet. We live not apart from the oceans but because of them, dependent on their capacity to regulate and sustain. Their warming is our warning, their resilience our chance, and their decline our responsibility. The great paradox is that what makes the oceans life-giving also makes them vulnerable. Their vastness, their depth, and their power have long made them seem eternal and unchanging, but now we know they are delicate in their balance. Every degree of heat absorbed, every current altered, every ecosystem strained, reveals the limits of their capacity to shield us. It is a reminder of how deeply our actions ripple through the natural systems that sustain us. To stand on the shore and gaze at the horizon is to look at the guardian that has kept our world habitable in the face of unprecedented change. Beneath that surface, unseen, lies the 90% of excess heat that might otherwise have transformed our world beyond recognition. The oceans have carried this burden, and in doing so, they have offered us both a gift and a warning. The gift is time, time to change course, time to recognize the consequences of our actions, time to protect what remains. The warning is clear, that time is not endless, and the oceans, though vast, are not inexhaustible. To speak of the oceans absorbing 90% of excess heat is not to recite a mere scientific fact but to acknowledge a truth about our age. It is the story of resilience and vulnerability, of silent protection and mounting strain, of a planet in balance and imbalance at once. It is a story that connects every life on Earth to the blue depths that cover most of our world. And it is a story that asks, with quiet urgency, how we will respond to the warning carried in the warmth of the seas. Beneath the surface of the oceans lies a realm of unimaginable diversity, a living library so vast that even the most ambitious explorers and scientists have only glimpsed a fraction of its contents. When scientists estimate that 91% of ocean species remain undiscovered, the figure at first feels implausible, as though it belongs more to the realm of fantasy than fact. After all, humanity has mapped the continents, catalogued countless plants and animals, and even ventured beyond the Earth into space. Yet the ocean, covering more than 70% of the planet, hides its secrets with quiet determination. Its depths are not easily penetrated, its ecosystems often remote, and its life forms adapted to environments hostile to human presence. What this statistic reveals is not simply a lack of knowledge, but a reminder of the ocean's vastness, complexity, and the profound humility required in the face of such mystery. The idea that so much life remains unknown begins with the nature of the ocean itself. Unlike forests, mountains, or deserts, which can be observed directly by human eyes, the ocean conceals almost everything beneath its surface. Light penetrates only a few hundred feet into the water, leaving most of the ocean shrouded in permanent darkness. The greatest depths are subject to crushing pressures that make human exploration extraordinarily difficult. Remote regions, such as deep-sea trenches, hydrothermal vents, and abyssal plains, are as inaccessible as distant planets. Even relatively shallow coastal waters hold secrets, teeming with species that may be too small, too cryptic, or too localized to have been properly studied. The sheer physical challenge of exploring the ocean explains why so much life has remained hidden, even in an age of satellites and robotics. Consider the numbers more closely. Scientists estimate that around 230,000 marine species have been formally described, named, and classified. These range from giant blue whales to microscopic plankton, from corals to deep-sea fish. Yet if the 91% figure is accurate, the true number of ocean species could be in the millions. Each undiscovered species represents not only an addition to a list but also an entire story of adaptation, survival, and evolution. Some may live in the icy waters beneath Antarctic ice sheets, others in the sulfurous clouds of hydrothermal vents, still others in coral reefs, seagrass meadows, or the open ocean's twilight zone. Each niche offers opportunities for new life, and the ocean's complexity ensures that most of it remains uncharted. The process of discovery itself is painstaking. Many species are small, requiring microscopes to detect and identify. Others live at such depths that only specialized submersibles or remotely operated vehicles can reach them. Even when organisms are collected, classification is slow, requiring careful study to determine whether they represent new species or variations of known ones. In some cases, genetic analysis reveals distinctions invisible to the eye, exposing hidden diversity within what once seemed a single species. It is not unusual for scientists to gather dozens or hundreds of unidentified organisms during a single expedition, most of which will take years to describe. In this way, the ocean's richness continuously outpaces human ability to record it. There is also the matter of scale. The ocean is not a single habitat but a vast mosaic of environments. Shallow coastal zones support ecosystems like mangroves and estuaries, which teem with life. Coral reefs, though occupying a small percentage of the ocean floor, host an extraordinary range of species. The open ocean, stretching between continents, appears barren at first glance but supports vast shoals of fish, drifting plankton, and great predators that migrate across thousands of miles. Then there are the deep-sea regions, covering more than half the planet, where life persists without sunlight, often relying on chemical energy from the Earth itself. Each environment holds its own suite of organisms, many of which remain unseen. What makes the statistic especially remarkable is that discoveries continue even in places thought to be well known. New fish are identified near popular coastlines, new crustaceans in shallow waters, new microorganisms in samples of seawater taken from harbors. This suggests that undiscovered life is not confined to inaccessible depths but may exist almost everywhere, overlooked due to its size or rarity. The ocean's complexity ensures that the familiar often hides the unknown. The implications of 91% undiscovered species are profound. From a scientific perspective, every new discovery expands our understanding of life's possibilities. Creatures from the deep sea, for example, have revealed unique adaptations to pressure, darkness, and scarcity, from bioluminescence to antifreeze proteins. These adaptations inspire technologies, medicines, and materials that benefit humanity. Marine organisms have already contributed to treatments for cancer, pain relief, and infections, and undiscovered species may hold keys to future breakthroughs. The ocean is thus not only a reservoir of biodiversity but also a potential source of solutions to human challenges. Yet this abundance also highlights a danger. If most marine species remain unknown, many may disappear before they are ever described. Human activities such as overfishing, pollution, habitat destruction, and climate change are transforming marine ecosystems at unprecedented rates. Coral reefs bleach and die as waters warm, plastic waste spreads into the remotest trenches, and acidification alters the chemistry of the seas. Entire species may vanish unseen, their existence erased before humanity had the chance to recognize them. The figure of 91% undiscovered species is therefore not only a reflection of mystery but also of urgency. It reminds us how fragile the unknown can be, how quickly we may lose treasures we never realized we possessed. For those who stand on the shore and look out over the ocean, this truth carries both wonder and responsibility. The waves may appear empty, the surface calm, but beneath lies a world so diverse that nearly all of it remains invisible to us. To imagine that the ocean is mostly known is an illusion. The reality is that we are still at the beginning of understanding its richness. The fact that 91% of its species remain undiscovered does not speak of ignorance alone but of opportunity, the opportunity to explore, to learn, and to protect before it is too late. There is something deeply humbling in this recognition. Humanity, for all its technology and ambition, has charted only the edges of the ocean's living map. The creatures that remain unseen remind us that the planet is larger, older, and more complex than we often admit. They remind us, too, that exploration is not only about distant stars or new frontiers in space but also about the hidden depths of the world we already inhabit. The ocean, vast and secretive, is a frontier still waiting, a reminder that the greatest mysteries may lie not beyond Earth but within it. To say that 91% of ocean species remain undiscovered is to acknowledge how much lies beyond our sight. It is a number that sparks curiosity, demands humility, and inspires both awe and caution. It tells us that the ocean is not a finished chapter in the story of life but a book still mostly unread, its pages filled with creatures that glow in the dark, endure crushing pressures, or drift unseen in the currents. It tells us, too, that in order to truly know our planet, we must turn our gaze downward as much as outward, seeking to understand the waters that sustain us. And it reminds us that discovery is not only about knowledge but also about responsibility, to explore with care, to preserve what we find, and to recognize that the unknown is not empty but overflowing with life. The Gulf Stream is one of the most extraordinary features of the world's oceans, a powerful current that moves vast amounts of water across great distances and shapes the climate of entire continents. It is often described as a river within the sea, a band of warm, swift water that originates in the Gulf of Mexico, flows along the eastern coast of the United States, and then sweeps across the Atlantic toward Europe. What makes this current so remarkable is not only its size and influence but also its speed. In some places, the Gulf Stream moves water at speeds of up to 5.6 miles per hour, making it one of the fastest ocean currents on Earth. This simple figure, modest when compared to the speeds of cars or trains, becomes astonishing when one remembers that it represents the steady, continuous movement of billions of tons of water, day and night, year after year, without pause. To imagine the power of such a current, one might picture a river as wide as a continent and far deeper than any canyon, flowing with immense force not across land but through the sea itself. The Gulf Stream can be up to 50 miles wide and over a mile deep. At its peak speed, that moving mass of water dwarfs all the rivers on Earth combined. It carries more water each second than the Amazon, the Nile, and the Mississippi together, multiplied many times over. The energy contained in such a flow is beyond human comparison, a vast engine of motion that redistributes heat across the planet. The speed of the Gulf Stream is not uniform. At its core, near the surface, the current moves at its fastest, reaching that remarkable 5.6 miles per hour, but on its edges the flow is slower, gradually blending with surrounding waters. Even so, the average speed of the current is still strong enough to be felt by ships and observed by satellites from space. For early sailors, the Gulf Stream was both a blessing and a challenge. Navigators who learned to harness its power could travel more swiftly across the Atlantic, saving weeks of time, while those who found themselves caught in its opposing direction struggled against its relentless push. Benjamin Franklin, fascinated by its force, was among the first to map its course in the 18th century, recognizing its importance for trade and navigation. His early charts gave mariners a clearer understanding of the invisible river that could carry them across the ocean or hinder their progress if they fought against it. The Gulf Stream's speed and strength come from a combination of factors: the rotation of the Earth, prevailing winds, and the differences in temperature and salinity that drive ocean circulation. Warm water from the tropics is funneled through the narrow straits between Cuba and Florida, accelerating as it is forced northward. The Earth's rotation deflects it to the right, keeping it close to the American coastline before it eventually turns eastward. This acceleration creates the fast, narrow current we know today. The warmth of its waters contrasts sharply with the cooler waters of the Atlantic, intensifying the flow and helping maintain its speed. The influence of such a fast-moving current extends far beyond the path of the stream itself. By carrying warm tropical water northward, the Gulf Stream plays a central role in regulating the climate of the North Atlantic. Europe, in particular, benefits from its presence. Without the heat transported across the ocean by this current, much of Western Europe would be far colder, its climate more like that of Siberia than the temperate conditions it enjoys today. The speed of the current ensures that this heat transport is continuous and effective, smoothing out extremes and making much of the region habitable. Marine life, too, is shaped by the Gulf Stream's rapid motion. The boundary where the warm waters of the stream meet the colder Atlantic creates zones of high productivity, rich in nutrients and teeming with fish. Migratory species such as tuna, marlin, and sea turtles use the current as a pathway, riding its flow across vast distances. The swiftness of the water allows them to move with less effort, covering hundreds of miles while conserving energy. Whales and dolphins also follow its path, finding food in the abundant ecosystems that thrive along its edges. The Gulf Stream is, in essence, a moving highway of life, carrying organisms across the Atlantic just as surely as it carries heat and water. The sheer speed of the current also interacts with weather systems in powerful ways. Hurricanes, for instance, can intensify when they pass over its warm, fast-moving waters, drawing energy from the heat that the Gulf Stream transports. The current also influences the position and strength of the jet stream in the atmosphere, creating ripple effects in weather patterns that extend far beyond the Atlantic basin. In this way, the Gulf Stream's motion at 5.6 miles per hour is not just a fact of oceanography but a force that helps dictate the weather people experience thousands of miles away. Despite its strength, the Gulf Stream is not immune to change. Scientists have long studied the possibility that climate change could alter its speed and stability. As polar ice melts and fresh water flows into the North Atlantic, the delicate balance of salinity and temperature that drives the circulation could be disrupted. Some studies suggest the current may already be slowing, though its surface speeds remain impressive. If the Gulf Stream were to weaken significantly, the consequences could be profound: altered rainfall patterns, disrupted fisheries, rising sea levels along the U.S. East Coast, and a cooling of Europe. The fact that water now flows so swiftly in the Gulf Stream is both a marvel of nature and a reminder of the balance that sustains it. There is something humbling about contemplating water moving at 5.6 miles per hour across such distances. Unlike the fleeting speed of a bird or the roar of a train, this is a constant, patient force, pushing ceaselessly with the weight of the ocean behind it. It does not tire, does not falter, and does not stop. It is a reminder that the planet is shaped by forces larger than human effort, that beneath our daily lives lie currents and systems that have flowed for millennia, long before the first sails crossed their paths. The Gulf Stream's speed is not simply a number. It is the heartbeat of an ocean, the pulse of a system that connects the tropics to the poles and continents to one another. It has carried explorers and traders, sustained ecosystems and civilizations, and shaped the course of history. Today, it continues its ceaseless movement, a river within the sea rushing at speeds that astonish when one considers the enormity of the waters involved. At 5.6 miles per hour, it is both gentle and unstoppable, a flow of warmth and energy that keeps the world in balance. To reflect on this is to glimpse the hidden machinery of the earth, to see in the speed of a current the immensity of natural systems that cradle life and guide destiny. The world ocean is far more than a vast expanse of water. It is the heartbeat of our planet, the cradle of life, and the force that continues to shape Earth's systems. It moderates temperatures, drives weather and climate, sustains an extraordinary diversity of life, and connects continents in a single, unified flow. Though it has been a source of food, transport, and inspiration throughout human history, much of it remains unexplored, holding mysteries and potential that stretch beyond our imagination. To recognize the significance of the world ocean is to acknowledge our dependence on it, for every breath of oxygen, every drop of rain, and much of the stability of our environment trace back to its influence. Its health is inseparable from our own future. In caring for the world ocean, we are caring not only for a vast and wondrous realm but also for the balance of life on Earth itself.